Hello everyone, and welcome. I'm excited to kick off this presentation on the fascinating world of analog storage oscilloscopes. Today, we'll explore what they are, how they work, and why they're still important in many applications. Over the next few slides, we'll cover their basic principles, features, and some practical uses. So let's get started and dive into the basics of this essential electronic instrument. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Today, let's take a closer look at the bistable storage oscilloscope. This is a fascinating device because it plays a crucial role in maintaining the state of a digital signal. Essentially, it can store a bit of information, whether a high or low voltage, until it is intentionally changed. This bistable nature means it has two stable states, which makes it ideal for memory storage and switching applications. Throughout our discussion, you'll see how this concept ties into the broader theme of digital electronics and signal processing. Understanding the bistable storage is key to grasping how modern digital systems retain and manipulate data reliably. This slide doesn't contain enough information. That's why we're moving to the next slide. This slide doesn't contain enough information. That's why we're moving to the next slide. Let's take a closer look at the digital storage oscilloscope. This type of oscilloscope has revolutionized how we analyze electronic signals. Unlike traditional analog oscilloscopes, digital storage oscilloscopes, or DSOs, use digital memory to store the waveform data. This means we can capture complex signals over time and then analyze them in detail at our convenience. One of the key advantages is the ability to freeze and examine signals, making it easier to identify issues or study transient events. Additionally, DSOs often come with advanced features like digital filtering, measurement tools, and the ability to connect to other devices for data transfer. This makes them incredibly versatile and essential in modern electronics testing and research. Overall, digital storage oscilloscopes are a cornerstone in helping us visualize, measure, and understand electronic signals with high precision and flexibility. The digital storage oscilloscope, or digital scope for short, is a type of oscilloscope that stores and analyzes signals digitally. What this means is that instead of just displaying the waveform directly, it converts the signal into a digital form, like ones and zeros, which are the fundamental building blocks of digital data. Ideally, it stores these signals as analog signals, but processed in a digital format for more advanced analysis. The process is pretty straightforward. The digital oscilloscope takes an input signal, captures it, stores it internally, and then displays it on the screen. This is a key advantage because it allows us to analyze signals more thoroughly and with greater flexibility. One of the most important features of digital oscilloscopes is their ability to store data. This means we can capture a complex or transient signal and examine it in detail later, which is often impossible with traditional analog scopes. They also come equipped with advanced triggering capabilities, enabling us to precisely select and capture specific events or signal conditions. Measurement functions are another highlight. They can automatically calculate parameters like amplitude, frequency, or rise time, saving us a lot of time and reducing errors. And of course, these scopes display signals in two ways: visually, on the screen as waveforms, and numerically, with exact values for different measurements. This combination makes digital storage oscilloscopes incredibly powerful tools for analysis, especially in complex or high-speed electronic systems, aligning perfectly with our goal of understanding and mastering signal analysis. Let's take a closer look at how the digital oscilloscope works. Essentially, it digitizes and stores the input signal, allowing us to analyze it more effectively. This process involves two main components: the CRT, or cathode ray tube, and digital memory. The CRT is used to display the waveform visually, while the digital memory stores the digitized data for further processing. If we look at the basic block diagram of a digital oscilloscope, you'll notice how these components are interconnected to facilitate accurate signal capture. The key to this process is digitization, which is achieved by sampling the input signals at regular, periodic intervals. This sampling converts the continuous waveform into discrete data points, making it easier to analyze and manipulate digitally. This ability to sample periodically is what makes the digital oscilloscope such a powerful tool. It allows us to capture transient events and analyze signals with high precision, ultimately connecting to our overall goal of detailed and accurate signal analysis. Today, I want to introduce you to the digital storage oscilloscope, a crucial instrument in modern electronic diagnostics. This device is designed to capture and store electrical signals digitally, which allows for detailed analysis and easy retrieval of waveforms. Unlike traditional analog oscilloscopes, digital storage oscilloscopes can record complex signals over time and then display them on screen for closer inspection. One of the key advantages is the ability to analyze signals post-capture, making troubleshooting much more efficient. They also often come with advanced features like waveform measurements, math functions, and digital filtering. Connecting this to our overall theme, the digital storage oscilloscope exemplifies how digital technology enhances precision and convenience in electronic testing. It's a perfect tool for engineers and technicians, aiming to diagnose and understand circuit behavior with greater clarity. This slide doesn't contain enough information. That's why we're moving to the next slide. The maximum frequency of the signal that a digital oscilloscope can measure actually depends on two main factors. The first one is the sampling rate, which determines how often the oscilloscope takes a snapshot of the signal. The higher the sampling rate, the better the scope can capture rapid changes in the signal's waveform. The second factor is the nature of the converter itself, meaning the quality and design of the analog-to-digital converter. A more advanced converter can accurately convert higher frequency signals, allowing for more precise measurements. These two factors are crucial because they directly influence the scope's ability to accurately measure high-frequency signals, which ties back to our overall goal of understanding how to effectively analyze signals in digital systems. Let's talk about sampling rate. To analyze an input signal safely, we rely on the sampling theory. This theory tells us that the sampling rate should be at least twice as fast as the highest frequency present in the signal. This is crucial because if we don't sample fast enough, we risk losing important information or creating misleading data. When we mention the sampling rate, we're essentially referring to how quickly our analog-to-digital converter can perform conversions. A higher sampling rate means the converter can capture more detail, but it also requires more processing power. Now, moving on to the converter itself. In our setup, we often use a flash converter because it's capable of very fast conversions. However, there's a trade-off. As the sampling rate increases, the resolution of the flash converter tends to decrease. This means that while we can sample quickly, the detail or resolution of each sample might be reduced. All of this directly impacts our oscilloscope's bandwidth and resolution. Higher sampling rates allow us to capture faster signals, but because of the limitations in resolution and bandwidth, there's a balance to strike. It's important to understand these constraints so we can optimize our measurement setup for accurate and reliable data. This ties back to our overall goal of precise signal analysis. By managing these factors, we ensure our measurements truly reflect the real-world signals we're studying. The need for analog-to-digital signal converters can actually be addressed in a different way, using something called a shift register. What happens here is that the input signal is first sampled, so we take a snapshot of the signal at a specific moment, and then stored temporarily in the shift register. From there, the signal isn't converted all at once. Instead, it's read out gradually and stored in digital form. This method offers a couple of key advantages. For one, it helps reduce the overall cost of the converter. Plus, it can operate at quite high speeds, up to 100 megasamples per second, which is impressive for many high-speed applications. However, there's an important limitation to keep in mind. When using a digital oscilloscope with this method, it can't accept new data during the digitization process itself. This creates what we call a blind spot, meaning there's a moment when the scope can't record any new information. Overall, while this approach offers a cost-effective and fast solution, it's important to consider this blind spot as part of the overall system design. It ties into our broader discussion of how different conversion techniques impact measurement accuracy and system performance. When visualizing the final wave, oscilloscopes often use a technique called interpolarization. Now, this might sound a bit technical, but essentially, interpolarization is about creating new data points based on the known data points we already have. It's a way to fill in the gaps and make the waveform look smooth and continuous. There are two main methods for connecting these points: linear interpolation and sinusoidal interpolation. Linear interpolation is pretty straightforward. It connects points with straight lines, giving a simple, direct approximation of the waveform. Sinusoidal interpolation, on the other hand, uses sine functions to connect the points, which can more accurately mimic the natural shape of many waveforms. This process is crucial for waveform reconstruction because it helps us visualize and analyze signals more effectively. It ties back to the overall theme of understanding and accurately representing wave behavior, ensuring we get a clear picture of the signal's true nature. In interpolation, the lines are used to connect the dots together, creating a smooth transition between data points. This technique helps us visualize the waveform more clearly and understand the underlying signal. When we talk about linear interpolation, it's often used for generating pulsed or square waveforms, where the signal jumps abruptly from one level to another, and connecting those points with straight lines makes the waveform look clean and precise. On the other hand, for sine waveforms, we utilize sinusoidal interpolation, which uses the natural smooth curve of a sine function. This is especially important when working with oscilloscopes, as it allows us to accurately reproduce and analyze the sinusoidal signals. Overall, these interpolation techniques are essential tools in signal processing, helping us accurately generate and interpret different types of waveforms. They tie back to the overall theme of understanding how signals are represented and manipulated in electronic systems. Now, let's take a closer look at some of the key applications of oscilloscopes. First, they are essential for checking faulty components in circuits, helping us quickly identify issues and ensure proper functioning. In the medical field, oscilloscopes are used for various diagnostic and testing purposes, highlighting their versatility. They are also crucial for measuring parameters like capacitance, inductance, and the time interval between signals, which is vital in many electronic applications. Furthermore, oscilloscopes allow us to observe the VI characteristics of transistors and diodes, giving us insights into their behavior. They're also indispensable when analyzing TV waveforms, helping troubleshoot and optimize television signals. In the realm of video and audio recording equipment, oscilloscopes ensure signals are correctly aligned and functioning smoothly. Beyond testing, they are used in designing circuits and conducting research, providing detailed visualizations of complex electrical phenomena. One of the more advanced features is their ability to display three-dimensional figures or multiple waveforms simultaneously, making comparisons and analysis much more straightforward. This capability is a reason why oscilloscopes are so widely used across various fields. Overall, their versatility makes them an invaluable tool in electronics and beyond. Let's take a look at the advantages first. One of the key benefits is that this technology has the highest bandwidth, which means it can handle large amounts of data very efficiently. This is especially important when we need fast and reliable communication. Additionally, the user interface is quite simple, making it easier for users to operate without extensive training. Speed is another major advantage. This system offers high-speed performance, ensuring quick data transfer and responsiveness. Now, moving on to the disadvantages. The main challenge is that this technology can be quite complex to set up and maintain, requiring specialized knowledge. It's also associated with higher costs, which might be a barrier for some organizations. In summary, while the high bandwidth, simplicity, and speed are significant advantages that support the overall goal of efficient connectivity, The complexity and expense are hurdles that need careful consideration. It's all about weighing these factors based on the specific needs of your project or organization.